Hi, I'm Prasad and I'm a postdoc. And today I'll be presenting my work where we studied magnetic fields in binary neutron stars. And we tried to see whether we can probe them through gravitational waves. And this work I did with Anushka and Piyush, who are my collaborators. The current gravitational wave observatories that are around us, they have seen two neutron star merger events. One is GW170817, and the next one is GW190425. And a lot of interesting insights has been obtained through this neutron star merger. The future is exciting because in future we will have some mega detectors, the Einstein telescope and Cosmic Explorer, which are 10-kilometer arm length and 40-kilometer arm length, and they will be seeing a large part of our universe up to large distances. And this large volume which they will be probing, we will be seeing a large population of binary neutron star mergers, and a lot of interesting physics can be investigated. And people are trying to see whether we can find the evidence of quark matter, whether we can study the tidal deformity of neutron star by large population that we'll be observing in future. And out of this many interesting questions, the questions which we are investigating is, can we use gravitational waves to study the magnetic fields of neutron star? So let's see what we have got. Neutron stars are compact objects which are 15 kilometers in radius, and they rotate rapidly, and they have magnetic fields around them. And the magnetic fields have been estimated to be 10 power 9 to 12 Gauss for typical neutron stars. And there are some very strong field neutron stars called as magnetars, and their magnetic field have been estimated to be 10 power 14 to 15 Gauss. The open question that exists is, what is the maximum field a neutron star can support? And there are some theoretical estimates using virial theorem where they calculate gravitational energy and magnetic energy. And the estimate suggests that the maximum magnetic field neutron star can support without getting disrupted is 10 power 18 Gauss. And this value is already 2 to 3 orders higher than what we have observed. So it may be that there are neutron stars of 10 power 16 Gauss, 17 Gauss, 18 Gauss exist, but we have not yet seen. We tried to see whether through observation, is there any indication for such high magnetic fields? Here there is a plot of the pulsars that we have observed, 3,000 of them. On the y-axis you have age, and on the x-axis you have the surface magnetic field. Each dot represents one of the pulsar. If you make a straight line fit to this data and extrapolate, then you can see that 10 power 18 Gauss magnetic field, it looks is possible when the pulsars or the neutron stars were quite young. So both the theory and the observation is suggesting that neutron stars with magnetic field 10 power 16, 17, and 18 Gauss may be out there in the universe, which has not yet been seen. And maybe through gravitational wave observations, when we'll be probing a large volume of our universe, this magnetic fields can be visible in these neutron stars. And also there are some other electromagnetic observation. For example, people have tried to put constraint using short gamma ray burst on the progenitor magnetic fields, which could be magnetars. And that constraint suggests that the magnetic fields could be of the order of 100 times 10 power 15, which is 10 power 17 Gauss, may be existing. And this type of constraints are also promising that there may be neutron stars with such high magnetic fields present in our universe. The neutron star binaries can get formed by two channels. One is isolated channel, where there is two main sequence stars. They undergo supernova explosion, and then there comes neutron stars. And these neutron stars in spiral for a lot of years, millions of years, and they come close and then they merge. In this isolated formation channel, the neutron stars are formed very farther apart, and they have to undergo millions of years of evolution. Even if they had very high magnetic field at birth, by the time they come and merge, the magnetic fields would have decayed to very lower values. But there is another interesting channel called as dynamical capture channel, in which if there are some dense clusters, like globular cluster, which has a lot of compact object, these two neutron stars, which are loitering very close to each other, may get captured with each other. And then the binary is formed at a very shorter distance. And the evolution time to merge is so small that if they had a very high magnetic field initially, that even at the time of merger, they will have high magnetic fields. The system of interest where we hope to find high magnetic fields is in this dynamical capture channel, because they had shorter evolution time. In the usual isolated evolution channel, the time scales would be so long that magnetic fields would have decayed to normal values. So what type of impact this magnetic fields will have? To see that, there can be two type of impact. When these neutron stars have magnetic fields and they're orbiting, and when they come very close, because of the magnetic dipoles, there can be some attraction or repulsion. Just like two magnets, if the south poles come up together, they will attract. If there is north and south poles will repel, and if there's a south and the north pole, they will attract. Similar way, when the two neutron stars come very close to each other, there can be an attraction or repulsion. The gravity is trying to bring them close, but this magnetic fields causing repulsion will oppose. If magnetic fields are misaligned, they will cause attraction, and that will aid in the inspiral. So based on the magnetic fields orientation, there could be an attraction or repulsion which will affect the orbital dynamics. And that is one of the effect. And the second effect is that these neutron stars have very high magnetic field and they're orbiting at a very high velocity, due to which there will be dipole radiation, and that will lead to some extra emission apart from gravitational wave, which will cause the shrinkage of the orbit. So overall, you can have an EM emission and a magnetic interaction, and this will change the orbital dynamics. And this has been studied for circular case by Ioka and Taniguchi. But since we are studying for dynamical capture systems, which will form by capturing the two neutron stars and they will have eccentricity, it's important to calculate this results for eccentric case, and that's what we try to do. We take a Lagrangian, we have the kinetic energy part, we have the potential energy part, and then we have an extra term where magnetic interactions are entering. And using this Lagrangian, when we calculate the orbital equations, this is what we get. This is the usual term, and then you have this particular correction term, which is entering, which you can see through gamma, where gamma depends on the magnetic moments, how they are aligned with each other, the dot products. If they are aligned opposite, it would be attraction. If they are aligned towards each other, there would be repulsion. And also depends on how they are aligned with the orbital angular momentum, whether they are perpendicular to the angular momentum or they are parallel to the orbital angular momentum. So overall, this is the correction factor, and that enters here. And we also calculated the energy radiated, and this is the expression you would have seen in any gravitational wave book, the classic expression 32/5. And in that, there are corrections because of this magnetic field. The 4 gamma term is a pure correction due to magnetic interactions, and there is an eccentricity and gamma coupling, which is coming because we are calculating it for an eccentric case. So because of this 4 gamma and this term, the energy emitted in the system would be different. For example, from this, you can see that because of the presence of the magnetic field, the energy emitted would be higher or lower depending upon the way the magnetic moments are aligned. Whether it is positive or negative will determine whether the energy emitted is more or it is less. So next, we calculated the phase of the gravitational wave, which is shown here. When the gravitational wave will arrive at our detector, it will have an amplitude and it will have the phase. The phase of the gravitational wave is here, and that also gets correction because of this magnetic term, the term 1 and the term 3. And we have shown here the dephasing. Dephasing suggests that in absence of magnetic field, what would have been the phase evolution? Now, if these magnetic terms are present, how the phase evolution would shift. And that's what the dephasing tells us, and that has been plotted. And here you can see for 10^15 Gauss, the dephasing, the change in the phase of the signal because of presence of magnetic field is very less for smaller fields. But if you take 10^16 or 17, the dephasing is substantial, of the order of 2 decimal place or even of the order of the usual phase evolution. And this is very interesting because if neutron stars of 10^16 and 17 Gauss exist, they will lead to phase shift in the GW signal a lot, and that can be observed. And through this, we can find the imprints of the magnetic field. So here we have shown the accumulated dephasing. What we do is that when the gravitational wave arrives, they arrive at 10 Hertz, and then the binaries keeps inspiraling, and then they merge. So we integrate the dephasing from 10 Hertz up to the particular end of the inspiral, and that is what is shown here. From this plot, you can see that for magnetic fields of 10^16 and 17, the accumulated dephasing is quite high, which is the integrated dephasing from 10 Hertz to the ISCO, where they stop inspiraling. And for smaller magnetic fields, it's a bit low. But for higher values of magnetic fields, dephasing is quite substantial. And also here, 2 situations are shown when the magnetic moments are aligned with the orbital angular momentum and they're on the plane. From this, it looks that when they're aligned along the angular momentum, the dephasing would be more significant as compared to when they're on the plane. And regarding the measurement prospects, what we do is that we take to study that whether we can distinguish the presence of this magnetic field. What we do here is that we take a waveform without magnetic field H, then we take a waveform with magnetic field, we take the difference, and that is this delta H. And the inner product of this delta H is taken, and if delta H is more than 1, it means you can distinguish the presence of magnetic field. If inner product is less than 1, it means you can't distinguish. And the inner product is defined here, where the detector information goes in the denominator. For example, we studied this with 3 detectors, the LIGO, which is currently operating with 4-kilometer arm length, Einstein telescope, which is a future detector, which will have 10-kilometer arm length. It's much bigger than LIGO. And the DESIGO is a space-based detector, which will be operating in deci-hertz band. And we have taken the 3 cases, and the distinguishability condition is studied. And you can see here, LIGO is in blue. It can distinguish magnetic fields of the order of 10^16 if it is present in the neutron star system. Einstein telescope can detect magnetic fields of the order of 10^15 if it is present in the system. DESIGO can detect magnetic fields of the order of 10 power 14 if it is present in the neutron star system. So what it means is that we can probe magnetic fields of the order of 10 power 14 to 16. LIGO can see only very high fields of 10 power 16 and above. ET can see even lower magnetic fields because ET is bigger in size, 10-kilometer arm length, and it can see lower fields. Why DESIGO is able to see 10 power 14? Because DESIGO is a space-based detector and it is operating at deci-hertz band, and it will. And here the neutron stars spend a lot more time in spiraling, and even the gravitational wave signal is longer. If the signal is longer and stronger, you can find even minute changes, and that's why we are able to find even smaller values of magnetic field imprints in DESIGO. So overall, LIGO can see 10 power 16, ET can see 10 power 15, and DESIGO can see 10 power 14. This 10 power 14 and 15 are already the magnetic fields. So it looks that through gravitational wave itself, we can measure the magnetic fields. This could be an independent way to measure the magnetic fields in future through gravitational waves, through ET and DESIGO, and through LIGO, we can see if powerful magnetic fields are present. And to conclude, here, very strong magnetic fields can be present of the order of 10 power 16 and 17, and that is allowed because neutron stars can support such high fields. Even the observational data, if we extrapolate, they are suggesting such high fields exist. And if this kind of magnetic fields are present in binary neutron star systems, and they are formed through dynamical capture, due to the shorter evolution time, even at the time of merger, these high magnetic fields will survive. But if they are coming through long evolution channel isolated, this magnetic fields wouldn't be there. In such dynamical capture neutron star systems, we try to study what will be the effect of the magnetic field on the energy and the phase evolution. And we found that 10 power 16 Gauss we can see in LIGO, 10 power 15 Gauss we can see in Einstein telescope, and 10 power 14 Gauss we can see in the DESIGO. It looks we can measure the magnetic fields in future through gravitational wave itself, and it could be an independent way of measuring magnetic fields, because currently we see the spin down of neutron stars and measure magnetic fields. This could be an independent way. Our next, what we are planning is that we're trying to do some Fisher matrix analysis and parameter estimation studies to see how well we can measure them. Yeah, thank you.
Thank you, Prasad. Questions?
So, like when you have these two like magnetars, pulsars, I mean, like these have to form in any of the star cluster, right? That's when they can be so close to each other. From the fact that they kind of formed in proximity in the star clusters, you do have an idea of their relative orientation, right? Like how their moments are aligned with respect to the like total angular momentum, right? It's, I mean, like here you take like there could be like multiple orientation.
Yeah. So in the sense that if they are forming through this long evolution channel, whatever their orientation, because of tidal locking and various things, they may change over the years because there's some millions of years of evolution. And the end, they may be aligned with the orbital angular momentum, and also they may be aligned with each other. But here, since the evolution time scale is very small, they may be at any erratic orientations. They may be, one may be aligned with angular momentum, another may be off, or both may be off with each other, and all that is possible. They may not have that much time. And also the systems are formed just by capturing. They were loitering near each other and they just got captured with each other. Any type of orientations may exist at the initial stage, and that may even survive until the last.
Okay.
That's I think.
But I mean, like when these stars formed initially, like they formed because of collapse of clouds which were nearby to each other, right? So isn't there any correlation between like these angular momentums of these collapsing clouds, like before formation?
I'm not sure, but in future, suppose we detected 100 such events, and we saw there was some particular way in which their angular momentums were there. They were always aligned or misaligned. Based on that, maybe we can comment on these things, that what is the properties of their progenitors and the particular blue black clusters where they were getting formed. So if everything we found that they were aligned with the orbital angular momentum, then maybe we can comment something. If they are misaligned, then we can, maybe observations will tell us that, or maybe simulations people have to do to tell something on that.
Any more questions?
Hello? Yeah. So I just want to understand, as the merger happens, the things will become very closer and closer. So in that very phase is how much the magnetic field is going to, will there be a significant change in the gravitational wave profile because the things are getting very much closer to each other. Is that taken into account in the model?
Like in the sense that, yes, like as of now, we have taken the magnetic fields effect, like in the sense that the gravitational wave will have a significant change. And that's what we are trying to see. That
No, I mean, in the very merging phase of two neutron stars getting very close to each other, how much of a change one could expect because of the magnetic fields?
Yeah, in the sense that we are studying only the inspiral phase. We are not studying when they collide with each other. We are just seeing the inspiral phase and using the inspiral phase itself, how the gravitational waves phase is changing. With that itself, we are seeing how we can find the magnetic field and the imprint of it. But very close to merger is not captured in our study because we have done it analytically. And what would happen very close to the merger that NR simulations have to take
Okay, I see.
into account.
And also in one of the formulas, you showed the coupling between the eccentricity and the effect of magnetic field. So can you physically give an idea about how is this?
Yeah, for example, this is the usual term for circular case which you have seen in textbook. And Matthews and Peters in 1960s, they derived the result for an eccentric orbit, and their derivation will have E square term and E power 4. So they have this 157/24 term, which comes because of eccentric. So these are like circular case with a correction due to eccentricity, and that's also known in the literature. And when I calculate it for circular case, if I would have done the calculation, I will get only the third term. I won't get the fourth term. Since I'm calculating it for eccentric case, I'll get this one more correction where eccentricity and the magnetic field are also coupling here, the magnetic terms. So that's how any particular expansion happens. This is a pure circular term. This is the eccentric term. This is the magnetic field term, correction to the circular part. And this is the correction where eccentricity and this will couple.
Okay, yeah, fine.
Thank you.